So this is a classic phase change problem, asking you the amount of heat to bring solid lead at this temperature to this temperature. This happens to be number 3 from the phase change practice that was assigned. I recommend pausing it right now and trying to do this problem. I'm going to go through this really quickly and then go through it very slowly and systematically after that. So here's the basic solution. First, you identify the points on the graph, and in order to do that, on the phase change graph, you need to identify from your table of values what the melting point and boiling point of the substance are. And solid lead has these melting points and boiling points, 327, 1750. Identify those key points. This tells me that I'm doing these 2 line segments. This is the phase change part. This one's the phase change part. This one is the temperature change part. So there are 2 terms, mH plus mc delta T. You plug in those numbers. The temperature change, there's no temperature change there. There's temperature change there. 1200 minus 327, you get 98,889 calories. That is 413,000 joules. Now, that was the quick version. Now I'll give a more, now I'll teach it a little more. Going back to the way the problem was originally stated, all this information that was just on the graph, you don't have that. And you kind of have to construct a graph, or at least construct a graph in your head in order to understand what's happening. So this is your typical phase change graph. What it shows is this period of time when you're increasing temperature, and I should label these axes. The temperature, you're going to hear people coming in and out because this is a classroom after all. This is temperature, and this is heat that goes in. And the key is that, generally speaking, yeah, when you heat something, it increases its temperature, with the exception of if it is undergoing a phase change, that's not true. So this segment here, this first segment here, this first segment here, there's an increase in temperature. That is when you have a solid that is reaching its melting point. Once it reaches its melting point right here, I'll use this dot as a pointer. Once it reaches its melting point right here, it then takes a lot of heat to completely melt it, and its temperature plateaus. Its temperature does not increase until it fully melts, and then now you have a liquid, and that liquid can, again, with the addition of more heat, increase its temperature. But it only increases its temperature up to a certain point, and then it's at its boiling point. When it's at its boiling point, it now plateaus, and you keep adding heat, and it doesn't increase its temperature. It does not increase its temperature. Its temperature stays constant while it is changing phase. Then when it's all transformed to a gas, now if you can somehow contain that gas, you can increase the temperature of the gas by continuing to add heat. You keep adding heat this whole time. This is still the x-axis is heat, but sometimes the temperature increases and sometimes it doesn't. Now, it's important to figure out the melting and boiling point. You look at your table and you see that they are 327 and 1750 for this particular substance. Okay, and those correspond to the plateaus in the graph. So now it says it begins solid lead at 327. Well, lead can be at 327 anywhere in here, but it says solid. That means it's all solid. So I'm starting there, and then I'm bringing it up to 1200 degrees Celsius. Now, not all the way up to 1750, but I'm bringing it somewhere to the middle of here. So I have 2 segments of this graph. Okay, there's this segment here, and there's this segment here. Now, each of those segments corresponds to an equation. If it's a plateau segment, it corresponds to a latent heat equation, which is this here, this mH. This mH means the mass times the latent heat. in this case latent heat of fusion, because it's a solid going to a liquid. It's also true if it's a liquid going to a solid. You look it up in the table. There's no delta T in the equation because the temperature doesn't change. It takes that much heat to get it just to melt it, and then it takes this additional heat to raise its temperature. But think about it. How much is it raising the temperature? It's raising it from 327 to 1200, so you subtract those. Add up all the heats and you get 98,889 calories, or if you did this in joules, you should get around 413 or 414,000 joules. That'll round a little bit differently depending. Here's a quick solution for number 4. Number 4, if you read it carefully, the melting and boiling points go from 1808 to 3023. You end up with 3 segments because it begins here and it ends here. So you end up with 3 line segments, an MC delta T that ends up being 1023, an MH sub V because it's heat of vaporization, and an MC delta T, and that delta T ends up being 477. That ends up being a large number, 5.9 times 10 to the 8th calories.